Okay, good afternoon, everyone. We will start our discussions on the week 5 content. I welcome you all to the weekly discussion of Smart Grid Basics to Advanced Technologies. This is Adyasha Sahoo, a PhD scholar from Department of Electrical Engineering at IIT Roorkee. So, in this week, basically, we'll go through the various islanding detection techniques and the protection issues that are arising in the distribution system due to the addition of this distributed generation. So, firstly, we see the concept of a microgrid. So, a microgrid is nothing but a miniature version of your bulk power grid that we had earlier. So, a microgrid has everything of a conventional that a conventional grid has, but at a lower rating or at a lower capacity, we can say. So, here you see you have the main grid, and then to the transformer, basically the voltage is stepped down here, and this is the PCC or point of common coupling of this microgrid with the main grid. So this microgrid is containing various generating resources. So you can see here, starting from we have PV, and basically we have, then this is your wind turbine. Then you have others such as biomass, micro hydro, and micro turbines. So these are all your generating resources. So these micro turbine and micro hydro, they are AC ones. So they are connected with the help of transformers. And then similarly for biomass generation, whereas you see PV is a DC source. So it is connected via a DC-AC converter to the AC distribution system. And then you have this wind. It is also generating AC power, but to control its various features, it is connected via AC-DC followed by a DC-AC converter to the grid here. You can see. Then these all are, renewable energy resources, and we know that they are uncertain and intermittent. So to manage them, we have a diesel generator also, so that whenever if these resources are not working, so it will act as a backup. Then these are all the generating side. In the okay, here you have also fuel cell, and we have a BESS also, battery energy storage, installed to handle the intermittencies or store the excess power from the renewable during their high periods and discharge whenever they are absent to satisfy the loads. Then you have various loads here. So all loads are AC type here. So this is a, we can say, a AC microgrid. We'll see in the next week or somewhere in other following weeks that there are also DC microgrids, and we'll see what advantage and disadvantage they offer. But right now, it is just a AC microgrid with its own small, you can say, distributed generations through connected through inverters and battery energy storage and supplying the local loads, their local loads. So, what are the key features of this microgrid? First of all, decentralization. So, we know that earlier centralized means so everything is controlled in one center, and you had power flowing from the generators to the loads. So, but with the help of microgrid, you have decentralized the grid. So, you have small clusters of microgrid at various geographical location, and they have their own generating resource. So, they are self-sufficient sometimes to basically supply their loads, and hence we can say that the grid is being decentralized now with various small clusters. Then resiliency. So this we have seen multiple times. So the resiliency and efficiency increases due to the addition of this distributed energy resources closer to the loads. Then it allows the integration of renewables, energy management. So this you have to install energy management system, popularly known as the EMS. So the function of the EMS is it has various controllers to regulate the voltage and frequency within the microgrid. So you know the due to the intermittent resources, so you need to decide at each and every point that whether the how the loads will be supplied, whether it will be through the batteries or which battery, if there are multiple batteries in the system, then which battery has to charge, which battery has to discharge. All these commands will be given through the EMS and controllers to the each specific device. And also they can change the set point of the inverters and other devices to regulate the voltage and frequency within the microgrid, and also to maintain the voltage and frequency at the PCC, at the point of common coupling where it is being connected to the main grid. Then the islanded mode of operation. So the microgrid has two modes of operation, we'll see. So first is the grid connected mode. So we had seen it in the previous slide where it was connected to the bulk grid through the PCC and through the transformer. Then the next one is the islanded mode of operation, which means that basically, so you see you have a relay here. So if this connection is cut off here, basically if you cut off this feeder or connection, then the microgrid is no longer connected to the main grid, and hence we can say it becomes a islanded grid operation. And then there is a transition phase between these two. Transition mode. So there will be two transition mode basically. One when it is transitioning from islanded mode to grid connected mode, and the other will be when it is transitioning from grid connected to islanded mode. So these are the major modes of operation. Another is also a black start mode that we'll see. Then next is grid support. Basically, since you have a flexible generations and battery energy storage with you, so now you can provide various services to the main grid because you have basically a flexibility with you now that you can variably change your basically demand or your generation to match the requirements of the grid. Here we see there are different modes of operation for the microgrid. So this first one is the grid connected mode where you have the support of the grid. So this grid connected mode is possible with or without the installation of battery. So in the grid connected mode, the microgrids can or cannot have BESS because the fluctuations in the frequency, the voltage, basically the fluctuations in the active power mismatch and the reactive power mismatch can be readily accommodated or basically absorbed by the main grid. So you don't necessarily need to install a BESS in the grid connected mode because there you have the support of the main grid. But in an islanded mode of operation, it is necessary. It is, we can say, must to have a BESS to handle the distributed generations that are installed within the microgrid. And you need also sophisticated energy management systems and controllers to operate in this mode. Then in the black start mode is basically when, let's say, the microgrid can sense that there is a fault in the main grid. So what it can do, sometimes we do what is called a intentional islanding. So it can island itself from the faulty part of the grid and it can supply locally its load. And whenever it can also, when the fault is been removed from the main grid, it will also support the operation of the main grid restoration. So that is the black start mode. Then a peak shaving mode and energy export mode. So these all we have seen in the previous lectures where we saw that whenever there is basically excess of RE, so you can basically you have two options. If you have grid connected mode, you can directly feed that excess power back to the main grid, or otherwise you can store it in your BESS. And similarly, in the absence or scarcity of RE, you can take the power required from the main grid, or you can discharge the energy stored in the BESS to supply the loads. Then demand response mode is basically to follow the grid commands. So basically, from the main grid, will request that we have seen in the earlier lectures, flexibility up and flexibility down services. So it will request, let's say that request to flexibility up service or down service. Then these requests can be, so if the microgrids follows the request of the main grid, so we can see it is basically the response of the microgrid to the main grid request. Then the next big issue that we discussed in this week will be the condition of islanding. So it is when the microgrid is basically being isolated from the main power grid, but it is functioning on its own, like the cluster of generation and loads that we call as the microgrid. So it is supplying power within its microgrid, but it is not connected to the main grid. That condition is known as basically islanding. So the islanding is of two types. One is intended, other is unintended. So intended islanding is basically to for the security of the microgrid. Like I said, whenever the microgrid can sense that there are some major grid disturbances or there are some major faults in the main grid, then to protect its own loads, what it will do, it will cut off from the main grid to protect itself because it is not having any problems. It is the healthy part of the system. So it will cut off itself from the faulty part of the system. That way, we can see the reliability or the resiliency of the microgrid will increase because the loads will get the continuous power supply from the distributed generation within the microgrid, installed within the microgrid. Then next is the unintended islanding. So in unintended islanding is because when again it is a type of islanding means the microgrid is being cut off from the main grid, but here that you have not controlled it due to some basically we can say unexpected conditions. So the microgrid has been islanded and basically it is not in the knowledge of the operator or anyone. So it is a dangerous situation because no one knows that this islanding has taken place. So it can lead to various disadvantages. So firstly, it can be a hazard for the workers or the repair crew members because they are not aware of the isolation of the section. So their safety will be compromised. Then this the various causes for this may be the incorrect relay settings, there may be some communication failures taking place, there may be faulty equipment, or due to any other technical issues. What happens is this unintended islanding can can take place. So, to detect this islanding becomes important to avoid its ill effects. So, it is very important that you first get to know that the islanding has been taking place at some location. So, what are the issues of this unintended islanding? First is the out of phase reclosing. So, what will happen because of unintended islanding is, let's say earlier this was the grid, and then to it you had a microgrid connected here. Okay, so here you have loads at different buses. Then you have also, let's say, your wind turbine, and then you have a DG, and you have a PV. So this is your microgrid. So let's say at any time instant t, the summation of the generating resources in the microgrid was, let's say, somewhat around, let's say, 2 kilowatt, and the total load in the microgrid, this is that in the microgrid. So let's say it is 1.5 kilowatt, which means what will be the grid condition? What will be the power flow in this feeder? Can anyone tell me? Whatever the mismatch of power in the microgrid, that will be the power from the grid, right? What it will be. What is the power mismatch in this microgrid? If I say the So if I say the in the microgrid, the total generation is 2 kilowatt and the total load available is 1.5 kilowatt, then what is the mismatch power in this microgrid? Power mismatch, we can say. So the delta P is nothing but zero point 0.5 kilowatt, right? And this zero point 0.5 kilowatt of mismatch is handled by the main grid. So this zero point 0.5, we know that 0.5 kilowatt is the power flowing through this feeder. Then whether it is injecting into the grid or absorbing from the grid. The grid will absorb the excess power here available, no, since you have over generation in the microgrid now. So basically, grid is absorbing or microgrid is injecting zero point 0.5 kilowatt. So that will then ensure the power balance within the microgrid. But once you have the unintended islanding, means this the grid will be now not present. So what it will lead? It will lead to your mismatches in the active power and similarly the mismatches in the reactive power also. And due to this, what will happen that you will have issues of voltage and frequency. Basically, issues of over voltage, under voltage, over frequency, and under frequency. So these may basically hamper the devices that are being installed in the microgrid. These further changes in the voltage and frequency may lead to the degradation of the power quality, basically. Then next is your grid protection interference. So that we will see in the coming slides that how this islanding will affect the grid protection schemes. Then inverter control mode switching. So this inverter control mode is nothing but a part of that EMS. So as I said, the main motive of this inverter is to regulate the voltage and frequency. And to regulate that voltage and frequency, what it takes feedback from the voltage at the PCC or at the grid, and it is fed into the control loops so that the voltage is regulated. But since now you don't have that correct voltage value with you, so it will again lead to the maloperation of the inverters also. Then malfunction of the protective devices. So we'll see that due to this islanding, there may be some relays may trip even if it is not a faulty condition. So we'll see it how different protection issues will take place due to this islanding. Then equipment damage because of this under voltage and over voltage and under frequency and over frequency issues because each volt rating or appliance each appliance has its own rating which is its working voltage. So if the voltage and frequency are beyond the permissible rating of the appliance, so it may lead to equipment damages. Then threats to the personal or crewman safety, so that we saw that if they don't know that this islanding has taken place, so they may when they reach the field, so they may face safety hazards there. Then next we'll see what is this relay non-detection zone. So basically, what is a relay? What is its function? Can anyone tell me? So it is a protective device, and its function is to basically sense the current that is flowing in the circuit. And whenever the current flowing in the circuit is greater than the threshold of this relay, so the relay will then give the signal to the circuit breaker to open the circuit breaker. So basically, this relay has a operating current rating. So let's say this is your main grid. So you have a, let's say, a relay here, and then followed by that you will have the circuit breaker. So the relay will continuously monitor the current here, continuously monitor the current, and it will be keep on checking that the current now, whether it is this, it will compare it with the relay operating current. And if this I is greater than the relay operating current, then it gives the signal to the circuit breaker to open the circuit, because it will sense that there is a fault. And if the current flowing in the circuit is less than the relay operating current, then the circuit breaker will remain closed because it is a normal operating condition. So here you see this delta P is here and delta Q is here, basically representing the active and reactive power mismatches. So at mismatch, we see as the difference between demand and generation, and similarly QD minus QG. So this is basically the operating zone of the relay. But here you see this is a threshold, we say. So this is the threshold for delta P. Similarly, this is the Q threshold, not for delta P, delta Q, and similarly minus delta B minus delta Q. So if the change in the active power is basically greater than this pre-threshold, then only this relay will operate. So beyond this square is the relay operating zone. But if the active power mismatch and the reactive power mismatch is less than this delta Q threshold and delta P threshold, like if it is somewhere here, the mismatches are lying within this square, then the relay cannot detect this type of faults. So this is called the non-detection zone of the relay. So our aim is always to minimize this non-detection zone to be it so that it is very small. Then next we'll see various islanding detection techniques. So they are basically passive. So in the passive, basically we are continuously monitoring various parameters in the circuit, and likewise we have the protection schemes there. In the active methods, what we do, we inject signals to through basically external resources into the circuit, and then we detect the landing condition. Then to basically these methods have some advantages and disadvantages of their own, this passive and active. So the hybrid method will combine the advantages of passive and active to minimize their disadvantages basically, and we get the hybrid islanding detect IDTs basically. Then lastly, we have communication based techniques. So there we will see that by using the various communication devices across your smart grid, you had installed PMUs and synchrophasers and many other devices. So how by utilizing the information from these devices, we can detect the islanding condition. So first, in the passive islanding detection technique, what happen is basically you monitor the electrical quantities such as your voltage, magnitude, voltage angle. Then you monitor the frequency, the impedance, or sometimes the sequence components also. So basically, we continuously monitor the levels of these various quantity, and then we compare with the predefined threshold. And if these quantities are greater than the threshold, then basically we say that the islanding has taken place. So here the challenge here is basically determining this predetermined threshold, because you see it is very crucial. Let's say your threshold for I threshold is 5. So as soon as your current is if it finds that it is 5.1, then you will see that it is the islanding condition. But this zero point 0.1 ampere current is very small. Even if it is 0.001, then also it will tell that it is islanding. So it is very crucial because you are basically uh, deciding this hard value or the hard threshold. So how to come up with this threshold value? That is the challenge here. So various type of passive islanding detection techniques are, firstly, it is the Rock-off, which is nothing but the rate of change of frequency, basically d by dt of your delta frequency. So here you are continuously monitoring the rate of change of frequency, and if there is a sudden change in frequency, then we say that the islanding has taken place. Then next is the voltage phase angle. So in the voltage phase angle is basically the phase angle difference between the bulk grid or the main grid and the DER, and we see if this phase angle is greater than a threshold, then it implies that islanding has taken place. Similarly, power quality. Basically, whenever there is a islanding, so it will lead to unbalance, and this unbalanced nature will lead to harmonics, and basically it will affect the power quality. With the islanding, what will happen? This harmonics will be more prominent in the waveforms of the voltage and current. So let's say you have three phases, right? A, B, C. So let's say this is the voltage waveform. Okay, so that was in grid connected mode. And let's say when the islanding will occur, what will happen is there may be over voltages in one phase, like this, or there can be also sustained over voltages. So such kind of waveforms implies that there are greater amount of harmonics present in the system, and it will imply that something is wrong. Then next is your positive sequence voltage impedance. So here basically you have the grid, okay, grid, then you have the PCC through the transformer here. Then you have this DER connected and also this load. So what you do, so you calculate the impedance of this line, this transformer, this line. So that is giving you the impedance between the main grid and the DER. What will happen when there is a islanding condition? So basically this part will be cut off. That means your impedance will be reduced because this feeder is no longer there. So that way, if you monitor the impedance, then also you can tell that a landing has taken place. Then next is the digital signal processing techniques, such as your wavelet transform. So here again, we analyze these voltage and current waveforms using techniques such as your wavelet transforms to basically study the patterns that are taking place. And if these certain types of patterns are observed, such as over voltage or that we say sag, swell, or interruption. Interruption means the voltage will be absent, like in B phase, basically. So we look for these things in the waveforms, and if such kind of waveforms we get, we can say that islanding may have taken place. The next type was this superimposed negative impedance based IDT. So basically, for an unbalanced network, so this ABC phases, they can be converted into your sequence component, which are your zero sequence component, positive sequence component, and negative sequence component. So here, what happens is basically you decompose this voltage vectors, basically both their magnitude and the direction, such that this ABC unbalanced quantities can be represented as your three sequence networks. So in the zero sequence network, basically all the three ABC phases, they don't have any phase difference with them. They are in the same phase. In the positive sequence network, basically in the positive sequence, so the same ABC phasor rotation takes place. That means if A is 0, your B will lag A by 20 degree, 120 degree, and C will lead A by 120 degree. In the negative sequence, what will happen? There will be anticlockwise rotation of the phasors. Basically, your if A is at the reference, then B will lead the 120 degree and C will lag by 120 degree. So this gives the clockwise rotation, this gives the anticlockwise rotation of the phasors, and their magnitude is transformed by this matrix, transformation matrix that we see 1, 1, 1, 1 alpha square, 1 alpha alpha square, 1 alpha square alpha. So here you multiply VA, VB, VC to get the V0, V1, V2. That gives you the magnitude of this sequence network. So what we can do is here the first step you see it is to acquire the voltage and current signals. So basically you have devices installed, so you acquire the signals and then you get the samples basically at a sampling frequency of they say 1 kilohertz, and then you do the phasor estimation using your weighted least square estimation technique, and then you compare the post fault impedance negative sequence impedance and the pre fault negative sequence impedance. So Z2 is your pre fault negative sequence impedance, and Z2 is your Z2 post is your post fault negative sequence impedance, and their difference is represented by this delta Z2. And then we have this index rate of change of your negative sequence impedance. So K is basically your sampling instant. So you see between K and K minus 1, that means the current and the previous instant, we are comparing this rate of change in the negative sequence impedance. And if this is greater than certain threshold, we can say that the islanding has taken place using this algorithm basically. See here, if this index is greater than the threshold, then we can say islanding is taking place. If not, then no islanding is there. Then next we have active islanding uh, detection techniques, active IDTs. So here what we do, we are basically injecting various signals. So first is this signal-based injection technique. So here we introduce external disturbances, which may be of low frequency or higher frequency. For generally we go for low frequency signals, and then basically after the injection of these signals, we monitor the behavior of the voltage and frequency at the PCC due to this external injection, and based on that, basically the uh, island detection scheme will work that way. And in the positive feedback technique, what is basically if you remember, so negative feedback will always in the control system, it will minimize the error and lead to stability. Whereas a positive feedback based technique will drive the system to instability. So here, knowingly you are giving positive feedback to the inverters and driving them towards instability to drive them to their unstable region, and then you will check whether the islanding detection has been taking place or not. Then next is this hybrid islanding detection technique. So here we basically combine both these techniques. So what we do, we will see the passive techniques. They are very simple because you don't have to do anything. You just need to monitor and compare with the threshold. But what was the disadvantage that it has a non-detection zone that we saw, and this threshold calculation is also not so easy. So what we do in this hybrid islanding detection technique is first you monitor using your passive scheme, and if the passive scheme is detecting that there is the islanding condition, if it is detected by the passive technique, then we get it cross verified using the active technique. We verify it by passive active technique, because these active techniques, there you need sophisticated device, also you need controllers, and majorly you are driving the system towards instability there. So you minimize the use of active technique this way, and you also verify the islanding detection of passive scheme. Then next is the communication based techniques. So here, since we had seen in the previous lectures that we have SCADAs and synchro phasers and PLCP where they communicate to the master station through your GPS, or they may be through the power line conductors or something like that. So they can actively monitor the status of the devices across the network. And if there is some islanding condition, so they can remotely also give signal to the breakers to basically operate according to the health of the system. So if we compare the various methods that we studied here, so this first one is a passive one. So here you have like rock off, the rate of change of frequency, rate of change of voltage angle, then under voltage relay, over voltage relay, under frequency relay, and over frequency relay. So the advantages is it is simple, it is cost effective, and it will have no power quality issues. But here the main disadvantage is basically the large non-detection zone that we saw. So if there is a islanding or active power mismatch to active power mismatch with this region, then this passive technique will fail to detect. Then the next method was your active method or signal processing based method. So here basically you monitor the voltage and frequency at the PCC using wavelet transform or S transform, and if there is a unbalance in the waveforms or instances of sag, swell, or interruption, so you can make out that the islanding has taken place. So here the advantage is the lower non-detection zone, and here also no power quality issues are there because here you are just analyzing the waveforms available at the PCC. You are not externally injecting any signals here. But what are the disadvantages? It requires higher processing of the signals because continuously you will be monitoring the waveforms there. Then next is your AI based techniques. So in the AI based techniques, you can use tools such as your ANN, that is artificial neural network, fuzzy based methods, or SVMs. But their disadvantages because they are difficult to apply in the practical implementation. Because first of all, you need to have huge amount of data sets with you to train this model and then apply it to the system, so which is a challenge here. And their advantages is they also offer lower non-detection zone, and they also do not have any power quality issues with them. So these were the passive methods. This is not a. Next, we discuss about active method. So here, first was this current injection based method, and second was the positive feedback method. So this we gave to the inverters. So here again, both these techniques they have very low non-detection zones, but the disadvantage is because of injection of external signals, there may be power quality issues. They may drive the system towards instability. So these are the major disadvantage of the active method. Then we'll see that what protection issues are there due to the addition of this inverter-based resources into our system. So there are four major issues. Firstly is the dynamics in the level of fault currents. Second is the bidirectional fault current, false tripping, and lastly blinding of protection. We'll see how the level of fault current varies with the addition of the DERs. So here basically this is the grid connected mode, and this is the islanded mode. Why is it so? Can you tell me? Why are we saying that this is grid connected and this is islanded? Basically, this breaker status it is open here. That means it is cut off from the main grid. So hence this is the islanded mode and this is the grid connected mode. So when it is in grid connected mode and let's say there is a fault taking place here. So you have three sources to feed this fault current. First is your main grid, second is your distributed generator G1, third is your distributed generator G2. So IGF is the fault current fed by the main grid, this. Then next is IG1F, that is the fault current fed by the source G1, and similarly IG2F, that is the fault current that is being uh, fed by generator G2, this one. So that gives you the total fault current. Then in case of islanded mode of operation, the fault current here is, since this is open now, so we have only two sources with you. So the fault current is the sum of IG1F plus IG2F. So now you can see the fault current value has reduced. So this, if I say I fault grid connected and this I fault islanded. So I fault grid connected is greater than your I fault islanded. That means there is a uh, decrease in value of fault current due to islanding. So due to this decreased value, basically this IAF may not be greater than your threshold, or the relay operating current may not be greater than relay operating current. So even if there is a fault, the relay will see lower value of fault current, so it will not operate even if there is a fault taking place. So this is one mal-operation, that is dynamics and level of fault current. So what will happen here? Basically, relay may not operate even during fault. Even during fault due to decrease in fault current. Basically, since the grid is not able to feed the fault, there will be decreased level of fault current. Then next is your bidirectional fault current. So here we see there are two locations of F1 and F2. So for this location F1, you see if there is a fault here. So you have two sources with you, G1 and the main grid, right? So this is your IGF1 from the main grid, and this is from the distributed generator. So both this fault current are in the same direction, you see, they are in the forward direction. So this relay will see that the current is flowing in the forward direction with higher magnitude, and it will trip. So everything is good for fault F1. But if there is a fault near to the circuit breaker here, that is fault F2, then the grid will feed it in this direction, and the generator G1 is feeding the fault in the opposite direction. So this is your grid, this is your G1 in case of this F2 fault. So now they are basically not in the same direction. Here you have bidirectional fault current, right? One in the forward direction, other in the reverse direction. So what it will do, it will basically again reduce the fault current, and basically the traditional overcurrent relay So they cannot differentiate between forward and backward uh, direction. They can not basically sense the direction of the fault current. So for them, the forward feeding current or the backward feeding current, they will be same. So if you have a traditional overconnect relay here, it will not work. So what you need to have to install directional relays. So the directional relay can differentiate between the direction of the fault current, and hence it can operate in a better way. Then next is your fault stripping. So here you see you have two parallel feeders, your F1 and F2. So there is a fault on this feeder F2. So this is the faulty feeder, and F1 is your healthy feeder. So again, the grid is feeding the fault, and also the generator G1 is also feeding the fault. So what will happen is, okay, this relay R2 will trip, and that we want. So what is the desired operation for this? Basically, to remove this faulty feeder from the healthy feeder, what is the desired operation for relay R1 and R2? Should R1 operate? So R1 should not operate because this is the healthy feeder. You don't want this feeder to get disconnected. So R1 should not operate and R2 should operate. So during islanding condition, what will happen? Okay, R2 will trip, but then this due to this uh, G1, there will this R1 will also sense this current that is being fed by G1 to the fault. So this R1 will also trip. So that is the fault stripping because the healthy feeder is being isolated here. We don't want relay R1 to trip, but since it is sensing the fault current that is being fed to the other feeder too, so even if it is not in feeder 1, this feeder 1 will also get removed. Basically, both these feeders will get removed. That is the fault stripping. Next is your blinding of protection. So here what will happen we see. So you have the fault here. Uh, without island mode, or we say grid connected mode. So the fault current will be IGF plus your IG small f. So that is the total fault current. But if you have a relay here, so it cannot basically sense this current IG small f. So this relay is only seeing the current IGF. So even if there is a fault, it may not operate because the uh, relay sensed current is only IGF, while the actual fault current is IGF plus time G small gf. So even if there is a fault, the relay will not operate, and hence we say the protection is being blinded because you have the G1 here ahead of this relay. So that's why it is unable to see the additional fault current that is fed through this source G1. So relay will not operate during fault as is sensing lower value of current than the actual fault current. So that brings us to the Q&A session. So the first question here is determine the superimposed negative sequence impedance at the PCC, where the magnitude of negative sequence impedance before and after islanding is given as 50 ohms and 70 ohms. You can unmute and speak, or you can write in the chat box, whichever is suitable to you. What was the formula for superimposed negative sequence impedance? It was delta Z2, right? Delta Z2 was, it was the post-fault negative sequence impedance and minus pre-fault negative sequence impedance. So what will be this? And we are seeing the magnitude on here. What is the post-fault negative sequence impedance given in the question? Before, after 50, 70. Can you tell me what will be the answer now? What will be the superimposed negative sequence impedance here? That will be 70 ohms. You see, post is 70 ohms. 70 ohm minus 50 ohm will be 20 ohms. Then the next question is the disadvantage of current injection based islanding detection scheme. Current injection means externally you are injecting some current to the network. So was this the passive technique or active technique? Current injection based technique. That is the active technique, active IDT. So, what was the disadvantage of active IDT? Any guess, any answer? You can type in the chat box also. So, this DR operates in unstable region. This disadvantage is also due to active IDT based technique, and this was due to the positive feedback based technique. Then high non-detection zone, it was in the passive IDTs. Here we have current injection base basically degrades the power quality because externally you are injecting currents. The correct answer is power quality degrades. The next is Q-axis current injection causes a sinusoidal component to exist in DAS during a landing position condition, whether it is voltage or frequency. It is frequency. We have seen that Q was related to frequency and P was related to voltage. Basically, change in active power will lead to voltage issues, and change in the active power will lead to frequency issues. In the non-detection zone, also we saw that. The penetration of the DER changes which of the following? Magnetic of fault current, direction of fault current, both or none. These we saw towards the last, right? The whole protection issues. Dynamics and level of fault current, it was magnitude change, bidirectional was direction, then fault stripping was direction, and blinding again was magnitude. So what will be the answer here? It's affecting both, right? We saw magnitude and direction. The next is if the over voltage relay trips, then what does it imply? Positive active power mismatch, negative active power mismatch, positive reactive power mismatch, or negative reactive power mismatch. So the formula for active power mismatch was difference between load and generation, active power, and similarly reactive power. For reactive power, it is QD minus QG. So if you remember the relay operating zone, so what does a positive active power mismatch imply? If delta P is greater than 0, then PD is greater than PG. If delta P is negative, then PG is greater than PD. So under this condition, what will be the voltage? Which case will be the under voltage one? Which one will be the over voltage? If there is a greater amount of load, that means load is not being satisfied, generation is less, that will lead to under voltage or over voltage. That will be under voltage, right? And similarly, if you have excess generation with you, that will be over voltage. So basically, if it is asked that if the over voltage relay trips, if the over voltage relay trips, then it will be delta P is negative. The delta P is negative. This is over voltage. This is your under voltage. So for over voltage, it is negative active power mismatch. Next question is, you have a microgrid with a 300 kVA load at 0.9 power factor, and you have a solar with 300 kilowatt. So the solar is connected through an inverter of 330 MVA. So what is the active power mismatch during high landing condition? So basically, you have been given that uh, instead of directly the active and reactive power, you have given with the apparent power, right? That means your SD is given as 300 kVA and your cos phi or power factor, whatever you call, is zero point 0.9. So from this, can you calculate the PD and QD? What will be the formula for active power using apparent power? That is your SD cos phi, that is your SD sin phi. So it is 300 times 0.9, and this will be 300 times sine of cos inverse 0.9. What will be it? It's 273 kilowatt. This is 130.8 kilowatt. Now coming to the generation side. So you have been given that solar generation PG is 300 kilowatt, this one. And then you have an inverter with a capacity of 330 MVA. So you have HG as 330 MVA. This is the KVA. Then what will be QG? That will be HG square minus PV square. So that will give you 137.5 kilowatt. Now here you have been asked the active power imbalance. So delta P will be PD minus PG, which is 270 minus 300, giving you minus 30 kilowatt. Then next is it is the same question, and here you have been asked the reactive power imbalance, that is QD minus QG, that we calculated here. What is QD minus QG here? That is 130.8 minus 1.5 kilo minus 6.7 kilo. So I hope these two questions are clear. Then next is which of the following is a disadvantage for a passive islanding detection technique? We have seen many times, right? For passive detection techniques, it's difficult to determine the threshold. They have large non-detection zones, and they will vary with load and inertia. Basically, this is a frequency, rate of change of frequency, and we know that the frequency is closely related to the inertia of the system. So, higher the inertia, lower will be the change in frequency, and lower the inertia, there will be greater change in frequency. Why so? Because when you have inertia with you in the system, So it can supply the change in the active power mismatch through the energy that is being stored by it in its inertia. That way, this active power mismatch will be reduced, so that in turn will lead to reduction in change in frequency. So basically, higher inertia will stabilize the change in frequency. So this rock-off detection technique will depend upon the inertia of the system. So the correct answer here is all of the above. Then the next question is a positive superimposed negative impedance applies what? Any guesses? This we saw in the earlier also. Superimposed impedance is nothing but Z2 post fault minus Z2 pre fault. So it is telling that this delta Z2 is greater than 0. It is positive. And this means your Z2. This means your delta Z2. So it is telling that if this delta Z2 is positive, what you can infer. That means your Z2 post fault is greater than your Z2 pre fault. Right? So that will imply V2 post fault is greater than V2 pre fault. So that means whether it is over voltage or under voltage. Post, sorry, yeah. So post fault voltage is greater means it is over voltage, right? Now, if there is a over voltage, that means whether it is which one is greater, generation or demand. There will be more generation, right? So if generation is greater than demand, then what will be the active power mismatch? Will it be positive or negative? It will be negative, right? So hence a positive superimposed negative impedance will imply a negative active power mismatch. The next is what is the limitation of AI based islanding detection technique? Power quality issues, large non-detection zone, difficult for practical implementation, or drive the system into unstable mode. Basically, there are no power quality issues because you are just analyzing the data here. You're not injecting any signals here. Then that AI-based technique also have lower non-detection zone. It does not drive the system into unstable mode. This was for positive feedback. The only thing it is difficult for practical implementation because you don't have firstly the data set, huge amount of data set available to train this model and also then apply these technique to the practical grids. Next is which of the following uses technologies like SCADA and PLCC to monitor the circuit breaker status? Passive IDT, active IDT, hybrid, or communication based techniques. So SCADA, PLCC, these are communication based techniques, right? Now, in a smart grid, the penetration of DR affects the level of fault current, direction of fault current, sensitivity of protection devices, or all of these. So these we saw, no? Everything level, that is magnitude, basically direction, sensitivity, all of these are affecting. So the correct answer is all of these. Which of the communication based techniques exhibit full control of both grid and the DG? Nothing but your SPD, right? Signal produced by disconnect. Then PLCC uses which type of energy communication signal along the power line? High energy, low energy, medium, or extremely high? They use low energy signal. Right? Now, basically, what are the set points for voltage relay for detecting the islanding? You have ranges for over voltage and under voltage. So for the set point, we have the over voltage as 1.1. That is, if the level of over voltage is more than 1.1 per unit, and if the under voltage is less than 0.88 per unit, then the relay will trip. Then, in which of the following IDTs the DR is driven into unstable mode? That was nothing but your positive feedback technique, right? Uh, then the Rokov based identity technique requires a minimum power mismatch of what? Basically, it is asking the non-detection zone. How much is the non-detection zone of Rokov? It is 15%. Basically, if your delta P is greater than 15%, then this identity work. But if delta P is less than 15%, it will not be able to detect the islanding. Then failure to detect the unintentional islanding will impose which of the following events? Malfunction of protective devices, equipment damage, threats to crewmen, or all of the above. This we saw initially, right? Firstly, this there can be malfunctioning of the protective device because the level of fault current, the direction of fault current, they may vary, and the malfunctioning may take place. Due to this islanding, what will happen? There will be basically over voltages, issues of voltage and frequency, basically, which may damage the equipment. Then, since it is unintentional, the crew members are not aware of the islanding, so their safety is also compromised. So, hence, all of the above is the correct answer. So, do you have any doubts, or maybe we can discuss something about inverter-based resources, as IBR? So, as we have seen in one of the questions of this mismatch, so basically there was a solar connected to an inverter, right? So why it is so? Why do we need an inverter? So your distributed generations or DRs are not capable of producing reactive power. So they only produce the active power. Then what is the issue? We all know that active power is a useful power. So even if the DRs are unable to produce the reactive power, what will be the issue that we'll face? So we know that to maintain the value of voltage and frequency, we need to balance both the active and reactive power. So the reactive power is also crucial in the transfer of this active power from generation to the source and to also maintain the overall basically stability of the grid. So hence the system also requires reactive power for functioning. Now That means we need reactive power sources in the system. What are the various reactive power sources in the system? So your conventional synchronous generators, or your SVC, that is a synchronous power compensator. Then the reactors, capacitors, and various other FACTS devices. So these are the traditional reactive power resources. Now, along with them, we are also mandating the distributed energy resources to support the system operation through the reactive power. So for that, inverters are required to produce reactive power and are hence usually coupled with the DRs and are hence installed with DRs. Now the next question is, how much reactive power support does the DRs need to provide? Next quantitative question is, how much reactive power support are the DRs required to provide? So there are various standards available, various IEEE standards, and there are different standards. So one such standard maintains that the inverter-based resources or the DER should inject the active power in such a way that the power factor is constant at the PCC. So that is commonly known as your constant power factor mode. So that means the P by Q ratio should be constant. That means as and when if the active power increases, if it is injecting more active power, that means it has also to support greater amount of reactive power so as to maintain the constant power factor. So this line will represent the constant power factor mode of operation. So the DRs cannot be in this region. They can only be their operating points will lie on this constant line, straight line. So a constant power factor of maybe 0.9, 0.95, uh, depending upon the standard, so that much they have to maintain at the PCC. Or the other kind of mandate tells that DRs must provide at least 44% of its maximum rated active power capacity. So what does it means? That when, let's say, the PDR is its P max, then at that instant the QDR should be at least 0.44 times of the P max. That means that let's say the P rating of the DR is 300 kilowatt, and if you install an inverter of 300 kVA, so what will this mean? This is 300. So if the inverter rating is 300 kVA, that means when P is 300 kilowatt, what will be Q? It will be S square minus P square. So S and P are same. That means it will be 0. That means you are not following the standard. So the inverter rating should be such that usually it is 1.1 times 330, I think that's. So if your P is 300 kilowatt and your inverter rating is 330 kVA, that means when, so this is your 330, but the active power cannot go beyond 300 kilowatt, right? Because this is its maximum rating. So it will be somewhat around 300 here. So when this power is Pmax, it will be able to provide this much amount of Q. So now Q is not 0, V is 300 kilowatt, then Q will be 330 square minus 300 square. That will give you something non-zero basically. So that gives you somewhat around 137.5 kVAr. And if you check basically 0.44 times 300 and 0.44 times 300 is somewhat around 132. So this is 132. So according to the standard, the inverter should be able to provide 132 kilowatt. And with an inverter of size 330 kVA, you are able to provide 137.5, which is greater than 132. That means you need to oversize your inverter, oversize the inverter by roughly 1.1 times the maximum capacity of the DER installed, active power capacity. 1.1 times the maximum active power capacity of DER. That will ensure that uh, you are following the standards of the system. So, due to this requirement of reactive power only, the rise of inverter-based resources, that is inverter installed along with DRs, is rising now, and various standards and mandates are coming up, which monitor that what should be the PCC voltage that they need to maintain, what should be the power factor they need to maintain at the PCC. So I hope all these words are clear. If you have any doubt, you can ask now. From the questions, numericals, anything. If there are no questions or queries for the session, then I think we can close now and we'll meet again for the discussion of week 6 next Saturday.